Welcome to the pre-recording of the second half of lecture 14, which closes off the fifth week of the 8-week summer course on computer algorithms. So we are also closing off the chapter on dynamic programming with the problem of computing all shortest paths in a graph, where the graphs are directed and they may contain now negative weights. That aspect of having negative weights will make that greedy algorithms will not apply. Okay, so what is our problem? We have given a graph. Every edge is directed, so which vertex comes first in an edge tuple matters. So I comes before j, and every vertex has a cost. Now, when we talked about shortest paths earlier, we were saying that the cost or the weights of the edges, they could be interpreted as distances. So, of course, a negative distance does not make sense. But as a cost, if you cost is typically negative, if you negate something negative, you end up with something positive. So we interpret a negative cost as a profit. Now, the same problem is the same question can be asked. What about the computation of shortest paths? Now, shortest no longer should be interpreted as in the terms of distance, so it's no longer that directly geometrically meaningful. However, this problem is still very interesting. And the first question we ask is whether a greedy algorithm works. So earlier in the lecture, earlier in this course, we covered Dijkstra's algorithm. Does it work? Well, let's look at an example. Why wouldn't Dijkstra's algorithm work? So here we have a graph with 4 nodes. It's directed, and we want to compute all shortest paths. Well, shortest path starting from 0. So what Dijkstra's algorithm does, we start at 0. That is the node that we have already explored. Then we look at the next node that has the that's closest to the node 0. So obviously we add 3 to it. And then the next obvious choice is 1, which has a cost 2. When we look at 0, 1, and 3, then the only choice is to add the edge from 1 to 2. So Dijkstra would select all edges with positive weight. Now, if you look, however, that edge with the negative weight, or if you like, with the profit of 6, gives you the shortest path from 0 to 3. So the shortest path from 0 to 3 has total cost 2 plus 3 minus 6, which is minus 1. So you turn a profit of 1 by going to 3 from 0 to 1 to 2 to 3. Okay, so fine, negative weights are indeed a problem. Can we not make all the weights positive? So if we compute in the graph, given with negative weights, we compute the smallest weight, and then we add W, that smallest weight, to all the edges in the graph. So here, the example we had, W is 3, so we add 3 to all the edges. And if you look to the graph of the left, the shortest path from 0 to 2 goes via 1. I'm sorry, does not go via 1. If you would go via 1, we would have total cost 4. But if you go via 3 and 4, your total cost is 3 minus 3 plus 3 is 3. Now, after the transformation of the graph, so adding 3 to all the edges, now you see that the path from 0 to 2 via 3 and 4 has total cost 12. Whereas now there is a shorter path. So if you transform the problem, then actually also transform the shortest paths. So, and again, what Dijkstra computes then would still not count as a solution. So greedy algorithms do not apply here, so therefore we have to look for dynamic programming. Okay, negative cycles are actually a problem. What is a negative cycle? Well, a negative cycle is a cycle. So what is a cycle again? It's a path where the first and the last vertex are the same. So we have a cycle, and the sum of the costs of all the edges in the cycle is negative. Now, again, negative is negative, but here in the world of costs, it's actually a profit. So this happens often in financial transactions where you would see every transaction as going from one node to another. So here is an example where you start at I1, you go to I2, I3 by a sequence of cells, and then you return to I1 with a net profit. So these graphs, so this is not an applied math graph, but these graphs are important from a certain application perspective. Okay, here is an exercise. This is exercise 4 in the lecture. So as I said, this is the second half of lecture 14. So we consider a directed graph with weights on edges. Generate an example of 9 vertices and at least one negative cycle. And then demonstrate the application of the breadth first search on your graph. So we've seen that the breadth first search on the graph, you can actually compute all the odd cycles. And that would be one algorithm to compute the negative cycles. Although you may now wonder what happens with cycles that have an even number of edges on it. The exercise is actually pointing at section 6.10 in the textbook. So something that we will not be covering. But if you have a graph and it has negative cycles, then you need to do something special. So that is a very important point here. The exercise in this course might not matter much, but I would just pointing at that the algorithm that we will cover, the Bellman-Ford algorithm, will assume that we don't have negative cycles. Let's first dwell a little bit. If we have no negative cycles, I mean, first of all, what happens if you have a negative cycle? Well, you could keep on running in the cycle, and what happens is that every time you do these things, your profit increases, or the cost actually decreases. So actually the question of in a graph with negative cycles actually has a very straightforward answer. The optimum sum is just minus infinity. And you have to keep on running through this. But so, I mean, in some sense, listing then that path will never end. And we deal only with algorithms here that run in a finite number of steps. Although we could say, look, running through this negative cycle is enough. that would actually solve it. So that's why the identification of the negative cycles is actually addressed in section 6.10 of the textbook. Okay, so now in a graph with no negative cycles, then we can ask, and this is a very well posed question, for the shortest path or the path with the minimum cost from an origin to a destination. And again, it's as small as possible for any path. So we cannot use a greedy algorithm. On the small examples that we see, you can see by listing all possible combinations what such paths should be. But we want an algorithm that is efficient, that will run for any graph of large size. Okay, let's then introduce the Bellman-Ford algorithm. And that was considered as one of the first applications of dynamic programming. So let's observe if we have in a graph with n nodes, if we have a source and a target, then if there are no negative cycles, then there is a shortest path that visits every vertex only once, or that means it has no repeat nodes. Okay, so let's prove this by contradiction. So we have a path P that is the shortest from source to target. If there would be repeat nodes, so we are assuming that that shortest path does have repeat nodes, then there are two cases. So the first case is that the path is not the shortest, so we can actually remove the repeat node. So if we are somewhere at a node and we come back to that node, then we can just delete it. So it will be a shorter path with uh, a fewer with fewer costs. Now, if you remove that cycle going back to a repeat node, and that would not be the case, then actually, so a path that is longer, a path that is larger cost, then actually you have a negative cycle. And we actually assume that the graph has no negative cycles. So therefore, we arrived at a contradiction in both cases. And therefore, if you have no negative cycles, then there is a shortest path that has no repeat nodes. Now, why is this so important? Well, it means that if we look at the statement again, we have actually not used that we have n vertices. But if we have no repeat nodes on a graph with n vertices, then actually this means that you can visit all the vertices at most once, and you visit all of them. So actually you have n minus 1 edges. So that means that we have a bound on the length of the shortest path. And that will be important to derive our our algorithm based on dynamic programming. So again, in dynamic programming, we explore the search space. So we are looking at the subspace of all possible shortest paths. And we need to have a clever way to reducing the size. And this important observation will help us. So, what does this mean? So, if we have, so we thinking again backwards always, we start at the end of the destination, and we have the minimum cost where you have at most I edges. So the notation OPT has been used frequently. It denotes the value of our objective function, what we want to optimize for a selection for a smaller problem. So where we have at most I edges. Now, the important observation said that we would never have to consider paths that are longer, that have more than n minus 1 edges. So we want to compute the optimum with n minus 1, starting from there. And now we need to express now we need to find a recurrence that links the original problem to smaller sub-problems. Okay, so here it is then. This is in some sense the key slide, the key idea here. So if we have the optimum path for length I, for all edges for I, so we have it, so we have the notation. So, but what can we say about this optimum value? Either we actually really use I minus 1 edges, and then actually it's the same. So for the optimum path that ends at the vertex V, um, we actually are using, uh, I'm sorry, we are actually not using I minus 1 edges, we're using I minus 2 or less. So that is the first case. Or we actually are using that many edges, I edges, but the we have the edge leading to V passes through the vertex W. Then the optimum value is then the cost of V to W, or it is getting to W. So then we have a recurrence of these two cases. We will select the minimum of these two cases. So either we do not have I edges, that's the first case, or we do have I edges, and then we reduce to I minus 1 edges by considering the vertex that actually starts from the vertex V. Okay, here is then the algorithm for the shortest path. And again, this is our last problem that we consider with dynamic programming. The long way starts with the recursive algorithm, which typically runs in an exponential time. But if we observe that we have so many identical subproblems, memoization helps us. In the memoization here, we have two parameters that control the recursion, the I and the V, the vertex V. Here we have a two-dimensional table M. M comes from the memoization, and we can derive a direct iterative algorithm based on how the memoized version actually filled in the table. Okay, so um, we have our table which we initialize. So we have the target or the destination vertex t. So for there we know that the distance is 0, getting to t from t. And we initialize all at infinity. We initialize the 0 row. So it's a row oriented algorithm where the rows indicate the length of the path, the number of edges in the path. So obviously, if you are not at the target, then and you have no edge that you're using, then you have infinity. That infinity is then useful to make the test work. As soon as you do have a way to get from to the vertex from the vertex V away, you the minimum with infinity is then that cost. Okay, so if you look at this algorithm, it definitely terminates and it runs in a double loop. So it has as many steps as there are edges possible in a shortest path. So this follows again the first loop is that loop that bound n minus 1 comes from the important observation. And we consider all vertices that where there could be a connection. So either again this recurrence reads that either your shortest path really has I edges, so that's the second case in this if, or whether it has one edge less. And the point is that we return the optimum value starting at the start vertex. Okay, so this will compute one shortest path from start vertex to a destination vertex. But actually the algorithm does a lot more, and here is this illustrated on an example on 6 vertices. So we know that we will have 6 rows in the table as we consider all paths from length 1 to 5. On the picture you can see that there are negative edges, so edges with a negative cost. If you go around that route, you make a profit. And we initialize, so the last column has our destination, vertex F. There, of course, a path of length 0 gives you cost 0. But if you don't have any edge, then the cost is infinity. Okay, so this is the initialization. Let's now go through the algorithm. So in the all the paths from length 1, we have a direct connection from A to F, where we make a profit of 3. Starting from A, we have a direct connection also from C, not from B. From D, we have 4, cost 4 directly, and from E, we have cost 2. So the first step is considering all edges that are incoming to our destination vertex F. Okay, then we apply the rule. So if we have a path of length 2, then there's no way we can improve in vertex A. That's what the application of the formula says. But now for B, you can see that there is a path that goes through E. And has a total cost of 0. C, there's only one way still how to do this. For D, you can see that the cost 4 can be reduced by going to A first. 6 minus 3 is 3. E can also be improved. You go to C and then to F. That's his cost 0. Okay, we run the formula again, and you see that there is some changes, so namely in A and B. So you improve by taking more edges, but where you also find a way to exploit the edges where there is a profit, where you have a negative weight. So you can go now with cost minus 2 from B to F. Okay, and I'm not directly seeing it, although it seems to me that if you go to D, minus 1, B to D, then to A is 5, minus 3 is not working. So the last exercise, the next exercise will actually be worthwhile to do. I will continue. You see that there is no change for starting from B. Now also there is a change when you start from D. So starting from D, it might now make more sense to go from D to A and then from A to B, um, where you then get a lower cost. And then D, A, B, E, F, that is the path. Okay, so actually the path starting from D is most interesting because there you have actually the longest path where you actually travel from D to F and you actually visit almost every node once because you have um, you have length 5, you visit exactly every node once. Okay, so this is how the algorithm worked. I try to explain it by looking at the picture. Um, but there is a systematic way now to recover a shortest path. A shortest path, and you can see that it has to, if you want the shortest path that reaches F, um, then you can answer this question from every vertex on. So start at, if you want the cost -6, so that's actually the profit 6 that you make, then this might be the path of interest. But the exercise asks you to recover all shortest paths, all shortest paths given the output table. So the algorithm returns only one value for one particular start vertex. Um, but with the table, we actually computed a lot more. So in some sense, if you're interested in only using a start vertex, then essentially you only would need to compute one column. But the algorithm actually needs to know more, so for the optimal path. So this is another question you could ask. The original question was compute the shortest path from a source to a target vertex, but you compute actually a lot more because you need a lot more. But the algorithm is still efficient. So here is the algorithm. The shortest path algorithm correctly computes the minimum cost of the shortest paths between any two vertices. So here I selected one fixed destination. So can you actually from the table read off the distance to any pair of vertices? This runs in cubic time. So for the running time, you have to consider that there are two explicit loops there, but then actually you need to consider all vertices different from the current vertex that you consider. So that minimum where you consider all the vertices not equal to the current vertex is a linear loop. Okay, so this concludes this lecture. I will end by pointing at the most important exercises. So here for this lecture, this was the last exercise, and also we have one exercise on the first part. Okay, so this closes then the chapter on dynamic programming, and this ends the 5th week in this 8-week summer course.